Oh, hi. I'd like to talk a little bit about the topic called stoichiometry. You probably just watched the module and just got finished studying the mole concept, talking about how many moles and how many water molecules are present in a student's sample of 18.015 grams. Let me put a balanced reaction up on the board here. This balanced reaction is done, how should we put it, on a huge basis every moment, because this is the combustion of octane, one of the components of gasoline. Cars, motorcycles, lawnmowers, industry generators are burning octane, which is a liquid. It's one of the components in gasoline. Oxygen from the atmosphere is being consumed, and we're pumping out of the tailpipe, as most people are well aware because of current discussions on greenhouse gases, carbon dioxide, and we're also pumping out water. I listed water here in the gas phase, and you can certainly argue, hey, water's a liquid at room temperature and pressure. Is water dripping out of the tailpipe on a cold day? Sure. But at the temperature that this reaction happens in the internal combustion engine, I'm showing that water's coming out as steam, water vapor. It's nicely balanced. On each side we have 16 carbon atoms, 2 times 8, 16 carbon atoms, 16 and just 1. We have 36 hydrogens, 2 times 18, 18 times 2, 36 hydrogens. For the oxygens, we have 25 pairs of oxygen atoms, 25 times 2, or 50. And on the right side, we have 18 and 32. 32 and 18 makes 50, so it's nicely balanced. Now, the reason that we need to study the mole is because this reaction is not written in grams. It is not true that 2 grams of octane will react with 25 grams of oxygen. That's not right. It's written in moles. It's written in ratios. 2 moles of this react with 25 moles of this. So the prefixes 2 and 25, and furthermore, 16 and 18 are combinations, counts. So we need to use moles. The reason we're not allowed to use grams, and grams fails us, is because the chemistry doesn't know weights, and these things all have different weights. It would be like saying breakfast in the morning is made by 2 parts bacon, 1 part bread, 2 parts eggs. It's not by weight. You're not comparing ounces of these things. You're doing actual counts. The chemistry is happening in counts. What I'd like to do is propose that if the student were to start with 3.5 moles of octane, we would like to find out how many moles of CO2 are produced, how many moles of water, and how many moles of oxygen are consumed. So the very first thing I want to do is draw like a little flow chart. I'm going to connect the moles of octane to the moles of oxygen. That's a matter of ratios. 3.5 moles of octane will react with some number of moles of oxygen. And we use these numbers out in front of our compounds, which are called stoichiometric coefficients. Some people call them ratios. Stoichiometric coefficient sounds really cool. It's too long. You'll get kicked out of parties if you say it. Here's what we're going to do. 3.5 moles of octane. I'm going to set up a conversion factor, and then out the right side go with moles of oxygen. We've been using conversion factors, things like grams per mole, atomic molecular weights, Avogadro's number. This conversion factor actually comes from the correctly balanced equation. Let me underline the values that we'll use for this particular one. 2 moles of octane react with 25 moles of oxygen. I just said 2 moles of octane. I know where that's going to go. It's going to go in the denominator so that the moles of octane cancel. In my haste, I left out the moles. On the top, we want moles of O2 to appear. That's what we're after. So let me put moles of O2 on the top. The number that we get, straight from the balanced reaction, a 25. So on your calculators, 3.5 times, call it 12 and a half. And I calculate a value of 43.750 from my calculator. Significant figures, I've started with 2 right here. These are exact numbers. The ratio is 2 to 25, not 2.01 or something strange. Those are integer values. So I need to finish up with two significant figures after doing multiplication. This gives me a chance to put a strange looking number. People in disciplines outside of science aren't used to seeing this. 43 rounds up to 44 because of that 7 that follows. And that number is 44 point, and I'm going to include the decimal place to indicate two significant figures. You could go ahead and do the others. Well, thanks for viewing these little modules, and let's leave with a bang.
Let me bring the candle up underneath the yellow balloon, which has hydrogen gas only, and the hydrogen is going to seek out the oxygen in the environment. So I'll bring this up slowly, slowly, This has the mixture of hydrogen and oxygen gases inside. This will happen a little bit faster. Let's see what the effect of that is.